And off we go with this idea of looking at what's called the first derivative test. Now, in the previous lesson, we talked a lot about one of the consequences of the mean value theorem being we can tell when a function is increasing or decreasing just by the sign of its derivative. And if you take a look at this particular graph, you can see that that is definitely the case here. This section, the graph is increasing between these 2 points because the derivative is positive. And here between C2 and C3, you notice that it's decreasing and the derivative is negative. And again, that makes a lot of sense because I could draw tangent lines that have positive and negative slope in those particular areas. Okay, so now this leads us to an interesting question, and that question is, can we tell where there are local maxes and local mins? Well, if you're looking at the graph itself, that's going to be pretty obvious to pick out local maxes and local mins without too much trouble. Don't forget that if it's a closed interval, we have to include endpoints as definite locals and possibly globals as well, but that's something for another discussion right now. Here's the big thing you're looking for. The big thing that you are looking for in deciding if a point is a local extrema is you are looking for a change in sign on f prime of x. You're looking for a change from positive to negative or negative to positive. And if those things are occurring, then you can identify if something is a local max or a local min. So take a look at this particular point right here. You notice that we're classifying it as a local max, and we know it's a critical point because the derivative is 0. So that's not really all that surprising. To the left, the function was increasing, and to the right, it's decreasing. So if a function is increasing and then decreasing, then it only stands to reason that that would have to be a local max. And you could make the same argument about this local minimum in reverse. If the function was decreasing coming into that critical point and increasing coming out of it, then the change from decrease to increase would signal that point would be a local minimum for sure. Now, it's entirely possible that a critical point is neither a local min or max, and that's something that you want to consider because you notice, like in these two cases that I just pointed to, there's no sign change there. So something to think about. Well, looking at a graph, that's pretty obvious how to find it, but what happens if you are trying to find the local extrema via algebraic and calculus methods? Well, let's take a look at that. And what we're going to do is we're going to create what's called a sign chart to help us out. So this idea is pretty simple. If you want to know where a derivative is positive and where it is negative, then sometimes we have to ask a slightly different question. In this case, that question is, well, what could possibly be 0? When could the derivative be 0? So you noticed that all of those critical points on the previous graph, they provided us clues as if it were a positive or a negative, or local min or local max, excuse me. So how do we find that out? Well, we need to find critical values first. So the first step in this little process is to find critical values. And I can't spell all of a sudden. All right, so here's how you find the critical values. Take the derivative, in this case 3x squared minus 12. Let's set that equal to 0, and let's solve it out. And I'm going to jump ahead and tell you that it ends up being plus or minus 2. You could probably verify for that for yourself without too much trouble. Okay, now the next thing to do is to make a sign chart. Now, this information that we just found is valuable because we now know where the derivative is 0. We know that at positive 2 and negative 2, the derivative is indeed 0. So, what I'm going to do is I'm going to create a number line and I'm going to mark off those two spots where there are -2 and +2. Now, you don't have to get too exact with your scaling here. It's just got to be functional for you, which is the important part. And it always helps if you mark an f prime of x here to help remind you which derivative that we're investigating when we make our sign chart. So, in order to complete this sign chart, what you need to do is you need to pick values of x, not critical values. And then what you need to do is put them into f prime of x and discover the sign at that point. Okay, so for example, I'm going to start on the left side of this number line, and I'm just going to pick a value. Let's just say x is -3. It's got to be less than -2. If I were to take that value of x is equal to -3 and put it into my derivative, -3 squared is 9, 9 times 3 is 27, and then 27 minus 12, that's 15. That would signal to me that we are looking at something that is positive. And every other value left of -2 is going to produce a positive derivative. All right, now let's pick something that's in the middle here. Let's pick 0. Let's just pick x, because picking x is equal to 0 seems like it would be a very logical thing to do. So I'm going to go ahead and plug that into my derivative, and of course, once I plug that into right here, I'm going to get -12, so that means everything in between is negative. Let's do the same thing for the right side here, picking a value greater than 2. Let's pick 3, and you're going to find that picking 3 is the same as picking -3. You're going to end up with something positive here. All right, so now we know where the derivative is positive, where it's negative. We know where the function is increasing and decreasing, but now we can also determine the absolute extrema as well. So let's summarize those. Let's start with x is equal to -2. Since we have a sign change from positive to negative, that's going to indicate that x is equal to -2 is a local maximum. And now that you know that, we can go to the other critical value, x is equal to +2, and since the sign changes from negative to positive, that's a signal that it's going to be a local minimum. Okay, so very important information here. Positive to negative is a max, a local max. Negative to positive is a local minimum. All right, let's investigate for a couple of more quick examples here how to find those maximum values. Okay, so let's try for this one, and this one's a little bit more, shall we say, interesting because we've got the product rule to deal with. So let's go ahead and find what the product rule looks like. U prime is going to be 2x, and then our v is going to be e to the x, and then I have x squared minus 3 times the derivative of my v, which is e to the x also. In order to solve this easier, I'm going to recommend, from an algebraic standpoint, that we factor out an e to the x. I think you're going to find that's going to make things a lot simpler to handle. Okay, and then we get a little quadratic that's stuck inside those parentheses, so let's rearrange the terms, and we will notice that that quadratic factors quite nicely. We're going to have x plus 3 and x minus 1. So that's the algebra that allows us to get a good answer here. Now, to find the critical values, we know two of them already. We know x is equal to -3 and x is equal to 1. We know those are critical values for sure. But what about this part right here? Well, the e to the x is always positive. Okay? That is something we have to stick in the back of our head, something we need to know about e to the x. that it is always positive. Okay, so if it's always positive, then that means it is never going to take on the value of 0. Now, if you're still having a little tough idea processing that, remember the graph of e to the x from your dirty dozen. You might remember it looks a little something like this. And it looks like it's going to approach 0 as you go towards negative infinity. So it's never going to be 0, and it's always going to remain positive. Okay, so good information to know. So these right here, the -3 and the +1, they appear to be our critical values. Let's go ahead and make our sign chart here. And as I go to pick values to put in the derivative, I'm going to show you a sneaky little trick. Let's pick something that's less than -3. How about we go ahead and pick -4? All right, so if I go ahead and plug this in, I want to remind you that I'm not interested in anything else but the signage. I couldn't care less what the actual value of the function is. I'm much more interested in the signage. So if this part right here is always positive, if I plug in -4 here, that's going to make this term go negative. And -4 minus 1 is going to make that go negative. So I'm going to have something that's negative, and a positive. And look, they're all being multiplied together. So a negative times a positive is going to end up with a positive value left of -3. All right, let's pick something between -3 and +1. Go ahead and pick 0. It's an easy number to work with. Again, that's always going to be positive. That's going to be positive, but this term right here will be negative if I put in 0 for x. So two positives and a negative multiplied together signal that that part's going to be negative. Let's pick something bigger than 1. Just pick 2, something really easy to work with. And you're going to get positive and a positive and another positive. So I am absolutely positive that's what the product sign is. Yeah, I probably had that coming from the crowd anyway. Okay, so now we know where the local extrema are. We know that at x equals -3 because we've got a sign change from positive to negative. We know that that is a local maximum. And at x is equal to 1, since again we have a sign change, but this time from negative to positive as we go from left to right, that's going to signal a local minimum. Okay, very good. One more example to look at this and see if we can come up with local maxes and local mins. Okay, now on this one we have to consider our endpoints, especially because on the left side, because it's 0 there and it's a closed interval on that part. So we'll tell you how to talk about that in just a little bit. Let's go ahead and find our derivative first. Our dy over dx is going to be 2 cosine x minus 1, and I need to set that equal to 0. And this could get real interesting in a hurry. Cosine of x is 1/2. Okay, so now I need to stop and think about what angles in that first trip around the unit circle have a cosine of 1/2. And one of those angles is pi over 3, and the other one is going to be 5 pi over 3. All right, now, is 0 itself a critical value? Well, no, it's not, but we're going to consider it an endpoint of our function. So as we go to draw our number line for our sign chart, I'm going to go ahead and put 0 at the left side. And then I've got all of these interesting angles that could work here. If I pick something that is between 0 and pi over 3, I'm pretty sure the cosine is going to be positive. If I pick something that is in the middle, let's pick pi over 2. Well, the cosine of pi over 2 is 0. So that's going to force this to be negative in the middle. And if I pick something bigger than 5 pi over 3, like say 7 pi over 4 or even 11 pi over 6, Cosine is going to be positive in that region. Pretty sure it's going to turn positive there. Okay, so let's talk about x equals pi over 3 first. That is going to be a local max because, again, we've got a sign change from positive to negative. And then at x is equal to 5 pi over 3, that is a local minimum. Okay, now what about x is equal to 0? Because we have to include our endpoint since we're dealing with at least a partially closed interval here. So when we start at 0, immediately we are increasing. The function will increase immediately as soon as x turns something greater than 0. So if that's the case, then this is going to be a local minimum. And the reason why is f of x starts increasing right away. Now, if it were decreasing, you could say it's a local max. Now, as you're going in on the other side, if you got a right endpoint, then that's something you have to consider as well. Okay, that's our little talk on how to find maxes and mins of the local variety.